Hello, everyone. Uh, Thank you for coming. I am Kashi, and I'm a program member for Greek and AI. We have been hosting this TrustML Young Scientist Seminar, which is a seminar series that features scientists and researchers giving talks and discoveries in relation with trustworthy machine learning, led by Jing Feng. Today is the 73rd seminar, and I am excited to have Dr. Jörg Wicker. Jörg is a senior lecturer at the School of Computer Science at the University of Auckland, founding CEO and the current CTO of MDCAP, and leads the machine learning group at the University of Auckland. Before his current role, Jörg had a postdoctoral position at the University of Mainz in Germany and earned his PhD from the Technical University of Munich. Jörg's research covers both the development of machine learning algorithms and their practical application across various domains, including bioinformatics, cheminformatics, and environmental sciences. His current focus is on reliability of machine learning algorithms, exploring adversarial machine learning, and addressing bias within the field. These works have exciting applications in domains such as chemistry, epidemiology, and environmental research. So today, Jörg will give us a talk about reliable machine learning, methods and applications in environmental sciences. So Jörg, we are very excited to learn about your research, and if you're ready, please begin.
Thank you. Thanks for the nice introduction. Thanks for hosting me here. And thanks everyone for coming. So yeah, I'm going to talk about, give an overview about my research and the research of my lab. And overall, I will talk a bit about what we do in adversarial learning in terms of reliability and what methods we develop there. And then I will briefly cover a few of our applications applied projects that we run. So probably most of you know what adversarial learning is. I'll just have one slide to give it an introduction. So in your typical machine learning workflow, you have your training process, and then you have your data, you do some pre-processing, you train your model, right? And then you have your model, you apply to new data, and then you have your predictions in terms of in the case of classification, right? And this all relies a bit that your data that you train on is representative on the data that you apply on later, right? So adversarial learning handles the case where that is not the case because there is some attack on something, and the attack can either be on the data you apply your model on, and examples can be modified such that your model misclassifies that example. So you do tiny changes to the example and modify it that's misclassified. Or the other case is that you applied you get the training data attacked in a way so that your training overall does not work, and your model by default produces misclassifications. So that slide is missing. And that mainly relates to the security threats, right? Someone could use your model and or modify the data and achieve something else, could modify your image classification and classify it in the wrong category, and that could have severe consequences. And as a starting point and motivation, I'll give you a brief overview of my first work in adversarial learning, which was a few years ago, which was we titled The Best Privacy Defense is a Good Privacy Offense. And this was connected to privacy on the internet, right? So we all use the internet every day. We use search engines, for example, we get results, but this is all free, and we pay by giving them our data and revealing a bit of our private information there. And they store their data and show you usually some personalized ads or something. And you cannot really avoid being part of that data set, right? You're one instance in that data set, and mostly Google or one of the big companies nowadays. And we were wondering, could you do something that you can keep using that, but somehow kind of attack your instance in a way that your data is so obfuscated that they don't know anything about you, that they misclassify you, right? Kind of an adversarial attack. Which is quite a challenge because it's Google and other big companies that do that, right? And how could you do tiny changes that you are misclassified? So the question is, you don't have access to their data really, right? You cannot attack the model and so on. and you rely on any feedback you have, right? So what you get from using, for example, any search engine is you get back ads, right? These things here. And these ads are a representation of what the search engine thinks of you. So depending what you search, you get different ads, but it's not only what you search, right? It's dependent on the query. So if I search here something about University of Auckland and Auckland, it's all related to Auckland. And here in this case, it's only related on Auckland because it's pretty clean browser profiles. But it also depends on your user profile, what they think of you, right? If Google knows that I often search for motorbikes, they will show me motorbike shops in Auckland as ads, for example. And it works the way that ads are assigned to certain categories, right? They have these hierarchical categories, and they assign users to these categories based on the queries they submit to the search engine. Now, what the search engines provide for you is example queries for these categories and these categories, because they provide that for advertisers, right? So we can use that we have these categories that they use and have certain example queries for these categories, and train a model that kind of predicts based on the query or some text, which category that text basically is on, a simple text problem. And because they provide a very good example data set, that works really well. So what we can do is, based on what they send us back, the ads, we can basically estimate what Google thinks of us, in which category, in which user category we're in. And that is great because we get a feedback and something you look into the data set and into the model, right? So what did we do with that? If you want to obfuscate basically our identity, it's this thing, which is basically a reinforcement learner. So the main thing is the circle here. You have the default case, the user submits a query and you get some results, the search engine results, but also some ads, right? And we implemented some agents that simulated users and basically generated queries, right? So we submit these queries to the search engine, we get some ads, and this part is kind of, we look at the ads and see which category in, so how the environment looks like in terms of reinforcement learning, right? So we classify the ads, which categories they're in, and then we have some actions, and these actions are, we choose a category from which we want to submit a new search query. And then we submit the search query to the search engine and see how well that worked. So how much do we confuse the search engine, right? How much do the ads change from our motorbike queries to something else, right? And we automatically search the category and choose the category such that it mostly best confuses the search engine. And we do that running over and over again, right? And we attack basically our user profile and modify our profile slightly such that the profile at the search engine is as different from the one we intend to. So we define some agents saying like, this agent is interested in motorbikes, and now make our category that we get from Google as different from motorbikes as possible. And we do that by automatically learning which ads are basically, or which queries do we need to submit to do that. And the feedback that we get is our are the ads and the categories we learn from. So this is kind of an adversarial attack, right? We attack the instance the model is applied to from Google, basically. And we do that over and over again, and we do small changes. We don't do big changes. We don't submit random noise. We submit very targeted adversarial noise. And we try to modify it slightly that Google doesn't realize that it's a big change, and we suddenly have some weird actions there because Google easily blocks you from doing something. And does it work? Yeah, it kind of works. It does something, let's say. Just not going into too much details here. You can see the red lines here is always when we train the model and let the agent run, and then we have some comparable methods where the blue is just submit random stuff all the time, and the green one is do the most extreme case, so a category that's always submit from a category that is most different, like from, I don't know, motorbikes to nappies or something like that. And you see the red line manages to slowly get a change and slowly go up there. In terms of score, the score is defined as being as how different your results from the search engine are from what you are intended to be. So how different from motorbikes are the ads that you get? The probability is probably that you are in the motorbike category, so that goes down as well over the ads. And yeah, and you see the comparable method, the random is we just submit random noise, and the green one would be the most extreme case, which you cannot really do because Google would just realize at one point there's some other noise coming in, right? And the red one is kind of the hidden adversarial noise that we submit. So it's a hard problem, and it's fighting quite against giants, right? But the cool thing is that we could trigger a reaction there. Were able to slowly change it. And that's what we really try to do there, right? We try to do tiny changes that are not detected by anyone. So that was the first work. We addressed it basically from the perspective, how can we make preserve our privacy and how can we obfuscate user profiles? And that were my first steps into adversarial learning. Then kind of used it adversarial learning or adversarial attacks to basically obfuscate your user profile there and basically attack the black box model where I don't have access to it, right? So that brought me then into kind of looking more into adversarial learning, and it kind of interested me, right? So why should we care about it, right? So there's obviously the security issue, right? You want to defend your method against people submitting weird queries on the internet, or other things, right? You want to defend your Tesla model against someone modifying your stop signs and so on. So that's obviously something you should care about. But also what I think is it's a really great tool to make your models more robust, right? Beyond the attack, even if there's not an intended attack. And I think it can have us really understand better how these models work, right? Some of them we don't really know, but looking at the predictions and how easy some changes do something in terms of adversarial attacks is really, I think, a great tool to help us how it works. And really making predictions more reliable, right? So going into models that are robust and produce predictions you can trust, right? And models that are kind of aware and somehow have a realistic estimate what your model can do. So not only predict, but know if you can predict. And you can basically look at it in the perspective of having an evaluation that goes beyond this traditional train test split, right? Because you can evaluate on non-existing data if you generate adversarial examples, right? You generate examples that are out of your data set and that are not existing, and you kind of can suddenly evaluate on something that is not there. And that's why I think it's a great tool to help you to make the model more reliable and robust in a way. So I agree that there are security issues you need to address, but what really interests me and fascinates me is the how can we use it to make it more reliable, or what can we learn from these adversarial attacks? So the work in our lab is looking at it from that perspective a bit. And I want to introduce a few algorithms we developed in terms of adversarial learning. And there are a lot around detecting adversarial attacks, so kind of understanding what these attacks do and what these examples look like, and how can you detect them, and how can you identify adversarial examples or poison data sets, and so on. So the first one goes into evasion attacks. So if you change test examples such that you produce a misclassification, right? And inspiration there we got from one of the research areas I'm also working on, from cheminformatics. And a little detour here. So in cheminformatics, we have this concept of applicability domain. Now, applicability domain, the motivation there is that the data space in chemistry is massive, right? You have billions of compounds. It's a lot of compounds. It's a really vast number of compounds. And it's very diverse ones, right? There's everything in this compound space. There are fertilizers in there, there's paint in there, there's flu medicine, some things that are very different from each other and have very different use cases. And the thing is that models that you train there, they have different uses and they never cover the whole space, right? You have billions of compounds. Experiments in chemistry are very expensive. So to generate data, you pick the domain you're in, like, I don't know, fertilizers, anything environmental and so on. And you have a subset of the space that is rather small compared to the really, really big data set that this really is. Now, the problem is if you take a data set and it's trained on a small subset of that space, right? You could theoretically, because compound is compound, so the structure is the same. You could apply it to anything in the space, right? But it wouldn't work because it's just you train it somewhere here and apply it to something there. Your model would not really work on that, right? And the concept of applicability domain basically defines a domain of that space where you can safely apply your model to. Right, so it says if the example that comes is similar enough, is in the domain of the model, then I can apply the model to it. And if not, I know this will not be working. And there was a relatively recent paper that introduced a nice method and that kind of combines the main ideas of this applicability domain into one, which is here, right? So it says the applicability domain consists of applicability, which the simple examples, the oldest example of applicability domain is just a bounding box around the examples, right? So if something is out of the bounding box, far away from the examples you trained on of your training set, then we won't apply the model on that because it's too different, it's far away, we don't know anything. Nowadays, there are more complex ways to do that, but this kind of was the original ideas of the applicability domain. And the second concept is that the reliability, and that is basically looking, what I want to show, hope to visualize here is the neighborhood of an example, right? If the neighborhood of an example is very clean, so it's only examples of the same class, then it's likely that it's easy to predict. Then the model is probably reliable. If the neighborhood is a bit more diverse, you have mixed examples of both classes, then it's harder. And the reason of that is kind of you are closer to the decision boundary, right? So it's harder to differentiate there. If something is neighbors only of one class, then you're likely in a space where it's easy to separate. And the last one is the decidability, which is based on the predicted class of the example, and also looks at looks also at the neighborhood of the example and how the distances to everything. And we thought that actually applicability domain and detection of evasion attacks, they share some interesting properties, right? So evasion attacks imply that the model does not cover the whole space, right? And is not sure everywhere. And you move the example basically usually over the decision boundary into regions where we're making bad decisions. And the applicability domain limits predictions in regions where the model knows not much about, right? Where it's a bit confused. So where we know it's not going to work and where predictions are hard, which is kind of exactly this thing evasion attacks do. So we wondered, can we use the applicability domain methods to detect adversarial detection, or the other way around, right? Because it's kind of, we try to do the same. We try to identify the points, the region in the space where we can detect something, or if something moved into a region where we cannot predict something, right? Where the model will fail. And turns out you kind of can. One method that came out of that was just published half a year ago now. We called BART, similar to the Google model, but our name was first. And it's 2 A's, so it's okay. And that uses exactly the method I explained before, right? A bit modified. So we check, we have our example and we check for applicability, and then we look at the distribution and how far we are away from the distribution. So do the input features deviate too much from the class now? So we look, is it far away from the distribution? And the second, the reliability, is the sample backed up by its in-class neighbors. So are the in-class neighbors very similar? And the decidability, does the output deviate from its neighbors, right? So are the neighbors different from the predicted class or not? And we don't use it as a staged approach, basically, but we use these 3 stages to combine them and then apply a logistic regression to calculate the score. And based on the score, you can say how likely it is that it's adversarial or benign. And so that's the one way we prove that it works, and we have a method that is pretty cool. That is, we detect adversarial examples completely independent of any method or training algorithm or anything you used, right? It works on any data. It's completely black box, doesn't need anything, and it just looks if examples are somehow in a weird region of the space. And the other way around, testing if our adversarial detectors work in chemistry as well. We're working on that, and we have results that show that it does. But yeah, we don't have fancy figures yet, so I didn't again. But coming with that we have now a method, right, that completely detects independent of anything, basically, just the instance and the data set, and we can see if it's attacked or not. We were wondering, can you transfer that to poisoning, right? Can we transfer that to a data set, basically to the case that you look at a data set that you want to train your model on and then say if it's poisoned or not, independent of the training method or anything? So most detectors of poison attacks depend on some form of ground truth, right? To have a clean set somewhere or something. So clean evaluation sets, some access to the model or something, or others then just detect poisoned examples. But we were wondering, could you just see based on the whole data set if it's poisoned or not? And then we developed the method that's called DIVA, which is currently submitted and hopefully soon published, which is a really quick method where you can apply to potentially poisoned data, and then it relies on nothing, just on the poisoned data to identify if it's poisoned or not. So how do we do that? We have our data set, and it's the input, and the output is it's poisoned or not poisoned, hopefully. Right, so, and how to do the method itself works is, so we train a classifier on our data set. Again, we don't know if it's poisoned or not, and we can evaluate it on our data set, just train test split and or cross-validation or something, right? And we get our, let's say, accuracy or performance of that. And in another step, we estimate our clean accuracy based on our classifier and the data set, and I'll come to that in the next slide, how we do that. And based on these, so we basically estimate how would the performance be if our data set were clean, right? And we calculated accuracy difference of these two. And again, apply a regression there. And based on the threshold, we decide, right? So the key step is we evaluate our model, calculate the accuracy on if it's poisoned or not. We compare to an estimated accuracy, and then we say if the difference is big enough, then it's poisoned or not. Now, the step down here, how do we do that? And there we use basically a database, and we use meta learning, and we generated a big database of poisoned and unpoisoned, clean and poisoned data. So we have our data sets synthetically generated or some standard data sets that you find online. We poison them, we train our classifier on them, and we evaluate them on a clean test set. And we calculate something called C measures, which is coming from meta learning. It's kind of a bunch of measures, 28 here, that describe the data set in some ways. It's something based on distributions, on performance, on something like K and N and so on. So there's a bunch of methods there that kind of give you features how this data set looks like, right? And we use the performance that we get from our evaluation here and put it basically in a new data set, right? And this data set consists, and the features are our C measures, and the target is basically our accuracy that we have. And so we have a data set, right? We can generate as many data sets as we want synthetically to generate a lot of data there. And so we fill this in our meta database, and we train a meta learner that then is able to predict us what accuracy this would be or which performance it would be if we would feed it in, right? So we know if it's a poison data set or if it's a clean data set, what performance would it be like, right? And this is the step down here. So, and then we have something that we would estimate what the performance would be, and we have another one that calculates what the performance is, right? And basically based on that difference, we decide if it's poisoned or not. Okay. And that works. And again, the cool thing is that we don't use anything, right? We train a classifier here, but it could be any classifier. If it's the classifier you use in the end or not, doesn't matter. You could use something very simple. And you'd use just a meta database that you have, or that you can generate for your data sets that are similar to what you have. And based on that, you can calculate basically and detect if your data set is poisoned or not. That could be a really quick and really useful pre-processing step before you go into training. And if there's a risk, that there's a risk that it's poisoned, and if something depends on that, you can run that first, and then you could look into which examples are actually poisoned. So this is a quick step that you could easily do. Good. So that was our work on detecting and kind of on understanding how these attacks work and how these attacks look like, and how evasion attacks, evasion example, sort of poison data sets or evasion attacks examples work like. And during that work, we also thought it came, sorry, there's no good connection, actually, I realize now. So we thought about domains where it makes sense, where adversarial learning could have some use, basically, right? And one domain we found quite interesting was time series forecasting, also, because there's a time series prediction forecasting has some interesting properties that if you think about, make adversarial attacks like an interesting case. And this was motivated by a research project we're working on for a few years with a PhD student, and now we have a postdoc working on that. And that is around the forecasting of ILI case numbers. And ILI stands for influenza-like illnesses case numbers in New Zealand. So in New Zealand, these case numbers are collected centrally. There are a few data sources we have to monitor them. We started this before COVID, and COVID is not very different from that, right? You get the case numbers and you get some curves. And it's some interesting things you note there. So this is the data sets we have, and it's New Zealand data. So our peaks come in the winter, which is obviously August, right? And these are different years that you see here that all have somewhat similar shape. And practitioners are really interested in knowing how many case numbers there are, because influenza and influenza-like illnesses is a massive burden to the health system and can be quite problematic. So in New Zealand, we go through that at the moment. We have quite massive waves of all kinds of influenza and other diseases because we were locked down and isolated from the world very long. And in general, our immune system is pretty down, so we are very prone to catching that. And the case numbers after the pandemic went really up. So it's really important to know how ILI cases will develop, and there are some mechanistic models that do that. So what you want to do is you want to be prepared to allocate resources, right? So if the numbers go too high, you need more hospital beds, you need to allocate health workers, and that's on different time spans. Sometimes our project partners are just interested, what is it next week, or what is in 2 weeks? Do we need more nurses next week or in 2 weeks? And the other thing is implement mitigation strategies, again, similar to COVID, right? So any vaccinations or masks, which people do you need to vaccinate? What do you do? Or extreme cases, you could do lockdowns, again, hopefully not. But any of these, what would make sense to implement, and where would you need to make sense to implement that? And yeah, so we have a bunch of data from there in New Zealand. It's a nice test bed because we're quite isolated, and you can, it's at the end of the world, we get tourists, but that's what it with visitors. So you have a quite controlled environment there to do that. And we thought of it in the context of adversarial learning with the mitigation strategies, right? So several mitigation strategies for ILI waves exist, and few are implemented, right? It's not, so we have something like vaccinations that are rolled out in New Zealand for different people for free, and other people have to pay for that. So universities typically pay for flu vaccines, pregnant women get free flu vaccines, and so on. Mask wearing is typically not implemented, and any stricter lockdowns not as well, right? So, but COVID showed us we have a quite broad arsenal of doing something against transmissions there. So the question is basically, which one is best to pick, right? We know that locking everyone up and doing lockdowns and closing the borders works quite well. We didn't have many case numbers during that, and worked well with COVID, but it's a quite extreme one, right? But what would be a good one to do? What was the best strategy, right? And you want the one that has the most effect, but the smallest, but had basically the smallest work or the smallest change to society, right? So decision at the moment is mostly based on expert knowledge and these mechanistic models, these simulations that they run. But we were thinking about how about adversarial learning? So our data is basically multivariate time series, right? So here's another data set from the 22 flu season in New Zealand at the moment and the different viruses that play a role. So we have these case numbers and we know what mitigation strategies are used, right? So that is kind of the second multivariate, the additional features of the time series. And the question that we basically ask is, right, what is the minimal change we need to do to have the biggest impact on the predicted values, right? And that is exactly the question that adversarial learning answers, right? We want to change the classification of our model into something else. And we want to do the smallest change because we want to do small changes so the attack is not detected. And in our case, if we assume we have a good model that predicts our case numbers based on our multivariate time series that reflects reality quite well, can we use somehow adversarial learning to attack that model and kind of by that attack reality and do a mitigation to the right vaccination in the right community group to have the biggest impact and lower the case numbers? And when do we need to do that? And what is the right time to do that? And therefore, with this motivation, with this thinking, we kind of started applying our adversarial attacks and our adversarial learning to time series, right? There's time series forecasting is kind of, I mean, if you think about it, it's just a regression in a way. It's auto regression is a pretty standard strategy, and with one method or the other, you use that. But what kind of is interesting is that you have kind of this overlap of training and test and the features and target values, right? Because what you typically do is you have your window, your time series, your time here on the y-axis, and you slide a window through that series. And you have your light blue one, which is the input window, and then your predictions with the orange one, right? And changes, if you would apply something to the real world, it would apply to multiple windows, the features basically, and changes you can do in the predicted values, again, might have an impact on your input features in the next one, right? So it's a bit hard to differentiate there between poisoning and between poisoning and evasion, because also you typically update your models from time to time and retrain, right? So how could you attack that? How could we do something like that? If you want to know what do we need to do, how do we attack an example to do that? Sorry, one more thing, right? What you want to do is this, right? You have the blue, that's your input features, and the orange here, which is the original prediction, basically. That's what your model is, hopefully very reliable. And if you do a standard attack that is untargeted, right, you would pretty random the blue dots here, you put pretty random up and down predictions, produce that, right? But what you would want to do is to have a very targeted prediction, to move something towards a certain point. And in the case of case numbers, you would probably try to make them as low as possible. And what you would want to do is a targeted attack that goes towards there and does not jump around all the time and change the case numbers. And because of the window, if you move it slowly towards this attack to this target, you might be successful. But yeah, you would need a targeted attack and not really an untargeted random attack that makes everything harder. So how can you attack it? We basically, there's a bit more work on time series attacks now, but it was not that much at the time we started. We basically just used methods from image classification, the fast gradient sign method or the basic iterative method here, and applied it to them, right? So what they do is you have your input time series, you have your model, and it predicts something, that's your forecast, right? And let's say this red X here is the target you want to achieve, and the orange is what you predict, right? And the fast gradient sign method basically works with the gradient and so on. And it applies a perturbation to the time series. So you add some values to the time series here, and you get your features that are slightly different, and then you get a reach target here, right? Or the basic iterative method is just an extension. It does iterative changes there. It does the same thing. So you get quite a few changes there, right? These changes, of course, are a bit harder to implement in time series because you have more days when you need to change something. You would want to do something which is quick, and has a strong effect, right? So what we developed is some adaptation of the pixel attacks, if you know them. So the pixel attacks in image classification is basically, it uses differential evolution to change just 1 pixel or 3 pixel or 5 pixel or so of an image to misclassify, right? So it's just an optimization problem basically out of it to misclassify, to change the classification of an image. And that is just based on single pixels. And that we found as very interesting for our problem, because single pixels would translate for us to single days, right? So changes on single days of 1, 2, 5, 3 days, whatever, would have an impact. So you'd learn on which days you would need to change something in your multivariate time series to do something. So we had to modify a bit, and the results called n vita for n values time series attacks. And in this case, it would be 3 vita, so we attack 3 days. So we would have our series, and you see, we would have only slight changes here on 3 days, apply to our time series, and then hopefully get our target done. And that's exactly what we're looking for, right? On which days do you need to on which days do you need masks on buses in this neighborhood, something like that, to limit the case numbers. And does it work? So yeah, we had some preliminary experiments on COVID data, because that's where we have a lot of data on mitigation strategies around the world and so on. And again, first of all, I'm not that kind of doctor, so don't trust me on implementing these. And it's probably just something you find in the data at the moment and nothing reliable. But you see, if you want to increase the case numbers or decrease the case numbers, you can with 1 vita getting 1 change, 3 vita getting 3 changes, 5 vita getting 5 changes. And you see these strategies that it would suggest something like here, new vaccinations on day 1 go, sorry, don't see it that well, up here from for 5 vita in this case, and so on. But this is again kind of something with all these more data mining methods, in a way you have to be careful if it's just something you find, right? Maybe it means if yesterday were a few more vaccination numbers, that means there is a wave coming anyway, and we need more, and more people go for vaccination and so on. But in the end, that would be our goal, to have something like that, right? To be able to propose these 5 changes you need to do, and that will reduce the case numbers, so increase the case number. Good. And with that, I want to go into environmental science, which was already our first application in environmental sciences, right? In population health, in a way, where we work in and try to predict those numbers. So our lab has many projects in environmental sciences, right? So we work a lot in environmental sciences, particularly in something called computational sustainability, in environmental chemistry, and health and environmental modeling. We work a lot in chemistry or environmental chemistry. It's a really interesting area. It's has very different problems to other areas. Data sets are really small typically, and that you find very often in environmental sciences. So we always look for really interesting and challenging projects, and they're really, again, a set of diverse problems, right? Typically data sets are small because it's expensive to generate data. Chemistry experiments are expensive. You have sometimes go every day to do some tests, and that's expensive. Or you have to go to a lake, take a water sample, go back, and it takes time to analyze that. So it's not that you have massive data sets and small data, which makes everything a bit harder to predict. You have the state of the art is probably often mechanistic or process-based models, and that's probably a bit part to it, that we don't have much data. So it's really expert-based models that write equations. And we have very diverse data types, often in the same application, right? If you look at water modeling, you have images from satellites, you have properties from the water itself, like chemical composition or something, or you have stream flow or the sludge types and so on. So very diverse data sets, and the data types that often that often combine in the same application. So it's for me, it's very interesting applications where, first of all, you can do something good with machine learning and AI, but it's also very challenging problems that are not that easy to solve. And yeah, so the first one I want to talk about is in atmospheric chemistry. That I started way back when I was still in Mainz doing my postdoc, and was probably one of the main works I did there during my postdoc. Now in atmospheric chemistry, the problem is that they look at the composition of the air, basically. So the air everywhere around us, it's full of small compounds, chemical compounds. They're called volatile organic compounds. They just float around, and they have different sources. They come from buildings, they come from traffic, obviously, but also in nature. Trees produce that, animals produce that, we produce that when we breathe out, when we move, just anything. It floats around everywhere. We breathe it. Most of them are harmless. Many of them are also quite dangerous. And environmental chemistry addresses that. So usually they go out in some areas and have a position our partners we work with have a sample station in the Amazon rainforest where they just keep on running some machines to analyze this concentration of these molecules and which molecules and how the concentration changes over time. And we worked with them on some project. They're looking at that, and what they want to understand the processes that happen in the atmosphere and where they come from, so they can measure all kinds of things. If there's a fire in the forest, they can see that, industrial influences and so on, and how that changes during the day and where it's going. And you can see quite a lot there. Now, the main work I did was not in the nature outside, but was in a cinema. So a bit more exotic. So what you have in a cinema is you have your audience, you have the screening room, and you have some airflow going through, right? Typically from the outside, you get some air sucked into the cinema and then out through the ventilation system. And in the cinema itself, you have some audience sitting. And what we did is we used this machine they use for measuring this concentration of the molecules, which is a mass spectrometer. And they plugged it into the ventilation system. So what we got is we got clean air from the outside going into the cinema. And then in the cinema, you have people sitting there watching the movie. And the air is sucked out through the ventilation system. And then we analyze the concentration of these compounds. And so the only source of these VOCs, these organic compounds in the air, is the audience in the cinema, because there's nothing else going on. Well, not completely, but I come to that. So why do we do that? So what do we get out of that? What we get out of that is that. So this is an example measurement we had. It was just CO2, carbon dioxide, which we produce when we breathe out, right? So, and this was our first measurement that we did. We did 2-3 of them. And over the time in, when was it, 2013, 2014, we measured the concentration of CO2 in the air in parts per million. So million parts, and how many of these are CO2. And what you get out of that is this, right? So we let it run over a year, over the Christmas period. And if you zoom in a bit here into one day, this is the 26th of December, you get these little shapes here, which we call shark fin shape. And if you zoom into one of those, you see this is one screening of one movie. In this case, it was Hunger Games, I believe, part 2 or something like that for that. And what you get here with specifically CO2 is the concentration in the beginning slowly raises when the audience comes into the cinema. And then you reach a plateau when the audience is stable in there, and we all produce the same amount of CO2. But you still get these tiny little peaks, ups and downs here, right? And then at the end, pretty quickly, everyone leaves at the same time, right? It's not like the beginning when there's still ads running and stuff, and they come in one by one. They all go when the credits start. And this is the movie that is running there. So we have, coming up here, we have a bunch of data with a lot of screenings here, all these little shapes that you have for screenings. And for each day, right? And we have different screenings per day of different movies. And not only for CO2, but for 400 of these compounds, basically, or 400 of these masses. So another example, or if you look into, let's look into CO2 a bit more. So this is the same data as here before. I just squeezed it a bit down, right? And then if you plot other days here of the next day and the day after that and the day after that, same movie screening at the same time, same as Hunger Games again, and same concentration of CO2. So if you look at them like this, and then you look at the peaks there, you see that they kind of perfectly align, right? And it's different days. There's no reason why they should be the same. There's just the audience in there. So you see that you can see the reaction of the audience to the movie and what is going on into the movie in the concentration of CO2 in the audience. And all these peaks there that you see, you can actually map back, and you can go back into the movie and look what's going on. And for this movie I did once, and all these peaks. The bigger the peak, the more intense the scene is, basically. And CO2 concentration raises if you're breathing more, if you're more excited. If you're sitting calm, then CO2 concentration is low. But if you're breathing more and more tense, then it goes up, right? So the bigger the peak, the more intense the scene is. You can look that up. There's somewhere, I don't know, burning skirt was somewhere, and I don't know, somewhere the main actress is attacked by monkeys. Where that was, and so on. So you can all find these peaks in the movies and link that back. And they are reliably in all the screenings. And even if you go into other days at different times, you find them again at the same time. So that's interesting with CO2, right? But we can kind of understand that, and that's pretty natural. But we don't only have CO2, we have 400 more. And here's some other examples of that we have. This is isoprene concentration, this is acetone concentration. Down here is ethanol concentration. And again, if I plot them for a few days that we have there, and again, it's only these 4 days I plot here and 4 screenings, but we have many more of them. So what you see there, it gets much harder to identify peaks because there's much more noise, right? You could look at them, but just by looking at them, you see some. The story behind these, so CO2 is just by breathing, right? You just produce it naturally. Isoprene and acetone, you produce generally when you use your muscles, when you walk around, when you work out, your breath contains more isoprene and acetone. So it kind of also makes sense that in some intense scenes, people maybe get a bit tense or use their muscles, and you can see that in the data. And ethanol is, alcohol. So we don't generally produce alcohol as a human body, but you can drink alcohol in the German movie, the cinema. You can get beer, right? So every peak that you see here is when someone drinks alcohol and it touches the tongue and it evaporates a bit into the air. So you can see basically all the time someone is drinking a beer here, or some bigger peaks is probably you spill it over and it's somewhere on the floor and then degrades slowly. So what can we learn from that? What do we want to learn from that? Not that much from ethanol. That's just an interesting thing to see when people need to drink in the film. But the overall, many of these VOCs that we have in the data set, like acetone, isoprene, or CO2, they're produced by us, right? And we have a cinema. So the people don't do much. They sit still. They don't look at their phones. They don't talk. The only thing they do is they watch the movie. And this causes something in them. So what we have basically is we measure in their breath or in their whatever they exhale or evaporate, we measure the reaction to the movie, right? So whatever we more or less feel, or can we kind of do that? Can we see in our data? Can we link that to the emotional stimulus that we have in terms of the movie? So can we basically measure how you feel based on the breath that you have? And yeah, we analyzed that. So we labeled the movies. That's what you see here. We did something like romantic scene, action scene, and so on. And we had our concentrations of our compounds. And what we did is again a time series prediction. So using that input, what scene there was and what the concentration of molecules was before, can we predict what the concentration of these molecules is next, right? And another model, can we predict what was just before based on the concentration of molecules in the future, right? So that's we call kind of backward prediction and forward prediction. And then we also did something, we proof of concept to make forward backward. And we use this time series classification again to analyze which features are important, right? Which of the concentrations is important to predict which type of scene was now, or what from before was important to do that. And the key findings basically are, yes, we can. So we can prove there's a relationship between the type of scene that's going on in the movie and what we breathe out and what the concentration of these are. We do find some interesting links. We find some candidates that are some markers for certain types of scenes or certain feelings. But we cannot say you breathe that out, so you're happy at the moment. But we're working on that. We have follow-up projects that look into other things. And yeah, this was award-winning research. We got the Ig Nobel Prize in Chemistry in 2021 for that. My proudest achievement. But yeah, it's we're still working on it. It's a really interesting project and really interesting data, and we have some more ideas to go into there. but yeah, aware of the time. I want to briefly cover cheminformatics and then just an outlook. So I think I'll need like maximum 5 minutes more. So cheminformatics, that's one of the areas I work the longest in, basically. And again, it's a really interesting area. There's a lot of potential for computer science. There's potential for AI. And one of my projects that I do since I started my PhD, and which then later came into started my startup company EnvyPath in Germany, is about biodegradation pathway predictions. So the motivation there is that you have a bunch of chemicals in industry or cosmetics or agriculture or pharmaceuticals, right? And these chemicals, sooner or later, they all go into the water. Some more direct, like agricultural, right? You put them on the field, fertilizers, they get washed out, go in the soil and then in the water. Cosmetics, after you shower, they go into the water, or otherwise industrial chemicals also a lot, and pharmaceuticals or degradation products of pharmaceuticals go there too. Now, this is a problem, right? You need to know what happens there in the environment. And some of them are a big problem, like pesticides or something. They are designed to do something bad. Some others, like shampoo or whatever, is designed not to harm you or someone, but it might be that it goes in the environment and it transforms into something else that is problematic for you. And they're in the environment, there are reactions happening in the water that transform them from one to another. So you should know what's going on. So compounds look like this, and what happens are these degradation pathways. It degrades from one compound to the other, degrades to the next, to the next, to the next, to the next, and so on. And it's really important to know what these degradation products are, because you don't want something harmless that degrades into something toxic that kills all the fish in the water, or you want something harmful like a pesticide that degrades into something harmless pretty fast, right? So it's really important for both industry and research to know those. Chemical industry really needs that to release the chemicals. It's in the EU, there are pretty strict guidelines to make experiments. And our partners that we work with, industry partners that we work with, use our methods that we developed as a pre-screening tool, basically, or plan to do that, to basically, before we do all this expensive chemistry experiments in lab, we do predictions to see, will this basically produce something very harmful? And if so, maybe we don't focus on this product. And the tool that we developed there is called EnvyPath, for environmental pathway prediction. And it's basically both a database and a prediction system for microbial transformation of organic environmental contaminants. So the database is generated over years and collected by experts in chemistry. And the prediction system is what we implemented on top of that basically predicts these pathways out of a compound. And so the database is basically open for others to submit data. So we collect data from chemists and for us to train models on. And the prediction system is basically a tool that they can use. And just briefly how the prediction system works. So we have our compounds basically, and we have something called transformation rules. Without going into too much details, you can imagine these transformation rules like regular expressions. They're just very blunt rules that say if a compound has this substructure, like a ring, which you might have seen here, these rings, right? Then it breaks it apart. Or if it has this chain here, then it adds an oxygen or something like that. So the expert-based rules, experts wrote them, and they're very generic, so they produce a lot of them, right? So if you have a compound, certain rules apply to them, like R1, R2, or 5, and Rn. And those are very general, so they produce too many products there. So what we do is we train models on them based on our database that give us predictions for each of these transformation rules, right? So we have machine learning models that take as input the compound structure and the transformation rules that trigger. And based on that, we predict the probability that this transformation, like a regular expression, remember, is a correct product. And this probability, we can then cut out basically the ones, in this case here, maybe R2 and Rn, that are not likely to happen in the environment, or that are not unlikely to happen. And that's a very simplification of what we're doing. We extended a bit. It's a small data set. Again, we have maybe 3,000 reactions in there. We have 700 compounds. And it's unlikely that this will get much bigger soon. And finally, I want to have an outlook. Something we're working on at the moment to build is a project again in environmental sciences and freshwater modeling. Maybe one thing here on sorry, jumping back. This is basically also the inspiration where the applicability domain and the links to adversarial learning came from, right? We looked into applicability domain here because the models are very limited, and there we built the links to adversarial learning there. Here, on the other hand, is a project where we want to use adversarial learning for certain things again. So it's freshwater modeling in New Zealand. We have a lot of freshwater, of course, like everyone, and we have many problems there due agriculture and other things. And we try to work with freshwater modelers to improve the models and to use AI and the combination of AI and these process-based models that they use to improve the modeling there. So what we have is not much data. Again, it's very distributed. We're working on combining that into a data source. There's no unified approach for freshwater modeling. We try to define with the Ministry for Environment in New Zealand to define standards how freshwater modeling should happen and how you can use AI for that. And what we're trying to do there, the key points are we try to combine these process-based models with our machine learning models, and then use this combination that we have and combine it again with adversarial learning to look for mitigation strategies similar to the flu and influenza modeling there, right? So what do you need to do to improve the quality of this river? What's the minimal change you need to do? Is it move that cow 3 meters up or something? And also we want to use adversarial learning there to improve the model reliability, point to problems in the model, find them where they are using adversarial attacks, and inform data collection, right? So where's the gap in the data set? Where's the gap that we need to address? Where do we need to collect data? Because data collection is really expensive. And yeah, last, identify the mitigation strategies for pollution. Yes, and with that, I'm done, and I want some acknowledgements. That's my lab with a bunch of PhD students. Thanks to everyone. Particular research here. Luke did a lot on the adversarial detection on DIVA and BARD. Mark did the time series for modeling. With Nuria, we were working on the influenza cases. Steffen just started working on that. Tim is my partner in Germany in the company working on the cheminformatics. Katharina, who's here, works on pretty much everything I do. She's a postdoc. Thanks a lot for everything there. A lot of partners around the world. I didn't highlight who works with us on what. EAWAC is a long partner in Switzerland. And yeah, we're sitting down here. And the last thing I want to say is come visit us. We're always happy to have people over. We have nice beaches and other things there. Always happy to host. And if you need a location for a sabbatical or just a research visit, come over, Peter. So thanks. If you have any questions, feel free to ask them. I put up a few links here. I didn't highlight the sources or everything. If you go to my lab webpage, which is the first link, you'll find all the projects that I talked about and with links to all the papers. Good. I hope that was not too long. Thanks a lot for listening.
Thank you for the next one. If anyone has any questions, you also have about 20 people online. So if anyone has any questions from Zoom, please.
Thank you very much for the talk. First of all, I'd like to ask about the data poisoning meta-learning. So when you train the meta-learning, were you able to get much kind of explainability from that model to be able to see like what makes a poison data set?
We didn't really look in. Oh no, we looked into that. We have some, so that we looked at the. There's back. I don't have the figures here, but I can show you, and we have them in the not published paper yet. We looked which features contribute and how they behave towards the level of poisoning, right? So how poisoned is the data set, and how do these C measures, if you remember these several features, link to that and how they behave over that. So you can see some of them react quite strongly, and some of them, of course, not. Yeah, right. But 28 of them we had, and there's some explanation there. I don't have that with me today, but yes, there are. You could see what features relate to poisoning and which not, and yeah.
So you can maybe use that to like, I don't know. Of course, using the actual the actual meta layer would be best, but like even just a kind of rules of thumb or whatever, I could be interested in. So,
You could do, but I see it also as understanding what poisoning is and what does that do and what can we learn about the models by that, right? Because that basically says poisoning and that breaks our model, and how does that relate to? So what does it really do in the data? What's going on? Yeah.
Cheers.
Can I ask a question about the cinema things?
Okay.
Very interesting. So I think you showed the figures for in page 32.
Yes.
Oh yes. So the shape seems similar, but the overall average seems to be different.
Yes.
Is it like the number of customers is different?
Yeah, exactly. So it's this is not normalized, right? So which day is the red one? It's 29th, I think. That's where most people were in there, right? So that concentration of CO2 in the room depends on how many people are there. So the higher the line, the more people are in there. Yeah. So you could just normalize it, and we did that for some cases by using the number of in the audience. We have the statistics for that as well. Yeah. So the height and the shape is different. The height is just really the number of people in the audience.
After this, I think you talked about forward and backward prediction.
Yes.
So the category is just the action and romance.
Yes. Sorry.
Is it kind of just classification?
So yeah, the back one is basically just a classification of the category of this action scene, romance scene, comedy scene. The forward is kind of a regression task because we try to predict the concentration of how the concentration will be, right? So the question we answer with the backward one here, let me remove that for a moment. So the backward was just to have a proof of concept and see that there is a signal. But the backward question that we answer here is, if we use basically it's a window of 5 minutes. So if you look at the concentration of VOCs in this 5 minutes, can we predict what happened just before? So what did they see before? So that's the backward prediction, right? So is that link there, and can we somehow explain which of these VOCs was responsible for predicting that it's an action scene or a comedy scene? And the other one is given, if I look what the people just, so similar question in a way, but what did we just see? So we saw half a minute of an action scene, which then moved into a romantic scene for 5 minutes. Can we predict the concentration of the VOC in the future? And then also kind of trying to answer the question, which is really hard. If you have the concentration of VOCs in the room, how will that influence the future concentration of VOCs? That's kind of the question. If I breathe out that I'm very excited that I am here, will Peter pick that up and be also excited about it, right? So will the VOCs I exhale, so will we transmit signals by that? Which we try to start answering there. We're doing some other experiments that go into that.
I see, thank you. I was wondering if you can do something similar for outside cinema, like in offices or
yeah. You can. I mean, there are some systems, and I know in offices there are some systems that look into mostly with CO2 for occupancy and stuff like that. But you could, I mean, cinema is a really nice test bed. We look for other places to make experiments after that. But the cinema is really nice because it's such a clean environment and such a massive number of audience, right? We had 400 people, 500 people in the audience. You don't get that somewhere else. That's why cinema is really nice. But application-wise, nothing stops you from using that in an office or somewhere else. Yeah, I know there are systems, and again, so we use this mass spectrometer here to collect the data. Where is it? Sorry, lagging a bit. There we go. And that's a really expensive machine, right? And that's really good to analyze the data and collect as much data as possible. But you can buy really cheap sensors that are $30 or something like that measure the same thing, just not that precise. So you could use that in offices to measure stuff, or in other places. And yeah, we got a lot of answers on questions on applications, like I know many were thinking towards security in airports or something like that. Yeah, but yes, you could use it in offices. You could use it at home. There's a bit of privacy concern as usual, but yeah.
Thank you. Any other questions? From the Zoom participants, if you have any questions. You can unmute yourself and ask directly. If not, let's end the session. Thank you very much for the great talk.
Thank you.